switch to number theory. Okay, so last time application was quite simple. So let's do one more application.
We aren't recording.
Recording in progress.
So let's do a slightly more non-trivial application. So this is the problem. So in how many ways can the vertices of a regular hexagon be colored using C different colors? Okay, so this is the question, and we'll use Burnside lemma to solve it. And recall that in this, what was the setting of the Burnside lemma? So there is some relevant group associated with your problem. It's like group of symmetry often, and for each member of the group of symmetry, you compute its fixed point on the set where it is acting, and then you add them and divide by the order of the group, and that gives you this number of distinct configurations that we are bothered in this line of problems. Yeah. So let's go ahead with it. So this is a hexagon, regular hexagon. So it's 1, 2, 3, 4, 5, 6. Okay. So this is a regular hexagon, and I think you will do it in this kind of things in your group theory course also, since you have R team. This group of symmetry should be a kind of a section in group theory. So here we will just highlight whatever we need for it. Okay, so let's. So this is the hexagon, and let's try to identify its group of symmetries. These things will be taught in rigorously details in your algebra course. Here we will not do everything. We'll assume a few informations and go ahead. But I'll give you like a working understanding of this problem, because otherwise it will be repetition. When you do the permutation groups, and you will also study group of symmetry in the course. Okay, so what are the group of symmetry? So this identity element is included, of course. Now, so this is like so this angle is how much? This is like 2 pi by 6. Right? So of course the rotations clockwise through 2 pi j by 6, these angles. So j is varying from 1, 2 to 5. This is the rotations, and then there will be some reflection, right? So let's look at a reflection. So if you connect like 1 to 4, this edge, yeah. So there you can reflect it along this dotted line, you can reflect it along 2 to 5. My drawing is not perfect, should be a straight line, and you can reflect it through these things. Yeah. So reflection about axis joining opposite vertices, that is 1, 4, 2, 5, 3, 6. This is a one set of uh, symmetry. What else is there? Think for a moment. There is another symmetry. So that's like if you take the midpoint and you reflect along that axis joining the midpoints of the opposite edge. Yeah. So reflection axis joining middle point of the opposite edges. There are three, right? So three of them. So you will study in the algebra course, like these things determine the group of symmetry of the hexagon. And rigorously proof there. Okay, so here our task is looking at this group of symmetry. We have to find the distinct coloring according to this group of symmetry. So we will use one side lemma for every member of this group of symmetry. We compute the fixed point and we add them and we divide it by the group size. So what is the group size? This is 1 and there are 5 here. So there are 3 plus 3. 3 according about the axis joining opposite vertices, and 3 about the axis joining middle point the opposite of 3. 6. So this is 12. So the size of the group of symmetry is just 12. So let's try to understand the fixed point, right? So since you are doing that permutation group, you know that each permutation can be decomposed into disjoint cycles. Yeah. And since that's in the cycle, you are rotating. 1 goes to 2, 2 goes to 3, 3 goes to 1. If there is a cycle, then if you think for a moment, it is very clear that on a cycle, your vertices should be labeled with the same color. Otherwise, it will not be symmetry, right? So that means a coloring is fixed by the symmetry if the cycles of the permutation that is you are using for the symmetry, they have the same color. Yeah. Some basic observation. Coloring. Shall I write it? Is fixed with respect to the symmetry if and only if all the vertices in each of the cycles in the permutation have same color. So now, what is a set that it is acting on? So what is a set? So that group is acting on the set X. What is a set? Set is the set of all colorings. So which is like every vertex can be colored in 6 ways, C ways, right? So the cardinality of X is C power 6. So this is a set on which the group of symmetry is acting, right? So that means, this observation means, if a permutation has k cycles, then it fixes how many coloring. Each cycle you can color in one of the COS, right? It fixes C power k colorings. That's the fixed point. Yeah. Right. Now let's try to compute the, so for the identity element. So for the identity element, what is the fixed size? Of course, it is C power 6, right? Because everybody is like a one cycle, 1 to 1, 2 to 2, 3 to 3. So for identity element, it is C power 6. The number of fixed. So let's take some example from this reflection group, maybe some rotation group from this group. So let's try to compute the rotation through 2 pi j by 6, and I'm taking j is like 2. So this is 2 pi by 3. So it will be rotated clockwise like this. So if I rotate, what will be the picture? So if you rotate, the picture will look like, it should be regularly drawn. I mean, I'm not able to draw exact regularly. So let's understand the cycles. So this is like, so what is the permutation? It was 1, 2, 3, 4, 5, 6, and one. This. So let's just write it. So 3 is changed to 1, so 1 goes to 3. I'm just writing in some way. 3, 4, 5, 6, 1, 2. So that means if you look at the cycle structure, this is 1 goes to 3, 3 goes to 5. So these 3 forms a cycle. 3, 5. And 2 goes to 4. And 4 goes to 6, 6 goes to 2. So 2, 4, 6 forms another cycle. This is just an example I'm taking. So that means the number of fixed coloring fixed coloring is this is COS, this is COS, so this is C square. It's clear? So how you are decomposing the cycle structure. I think it's a good exercise to take that one from the rotation group and one from the reflection. It's the same computation basically. So you can reflect this axis joining opposite vertices, and you can reflect the axis joining the opposite edges. So it's an easy exercise that for reflections of vertices along the axis joining opposite vertices. So let's say 2, 5. Vertices. I did the computation, you can do it. I think it has 4 cycles. I'm just not doing it, it's mechanical. 4 cycles. And for reflection along the axis joining opposite edges has 3 cycles. So this is the description, and for the rotation, all the other computations are similar. I just did for j equal to 2. You can do it for all the values. So now basically if you list down, so this is my identity, and sigma 1 means rotation via 2 pi by 6. Okay. Sigma 2 means rotation by 2 pi by 3, because the j value is this j value is 2, j value is 1. And then you can list down sigma 3, sigma 4, sigma 5. These are the j equal to 1, 2, 3, 4, 5. And then you have these reflections along the vertices and axis. Let's give them some name. There are 3 of them. I'm just denoting by them tau and delta. So remember that there are 3 taus, 3 deltas. So this is c power 6. This is just c. This we computed c squared. This will be c cube. This again c squared. And this is c. And each of these tau, so this is 4 cycles, so c power 4, and delta will be c power 2. Now by Burnside lemma, what will be the thing? So this will be c6 plus 2c, 2c 3c4, 3c cube plus 1c cube. That's like 4c cube. That I missed. C squared, 2c squared. So this is the different colors. And notice one very beautiful thing is that so number of colorings must be an integer, right? That means whatever the value of c that you put, this polynomial equations always divisible by 12. C power 6 plus 2c plus 3c power 4 plus 4c by 2c squared. Yeah, so this was one example I could not finish in the last class. So as we discussed, we will not go to the Pouillet's counting theorem because there are not much time left for the course now. Yeah, I guess this was what I wanted to do today. After that, we will start number 3.
Recording stopped.
So you can practice a few problems from the textbooks on this quant-site lemma application. Recording or shall I start?
Yeah, I can record.
Recording in progress.
Okay, so today we will begin with a new module which is on number theory. Okay, so I believe you haven't seen a course on number theory yet, from what I learned, right? Is that right?
Yes, ma'am.
Okay. Yeah, so we will begin with like real basics of number theory, and we'll see some very interesting applications to computer science, especially cryptography. So that's what the plan is. Okay, so let's begin with some stuff. So we are all familiar with division, right? So mostly we will look at integers, at least in this module, although many of them apply to other fields as well. But we'll be dealing only with integers. So we will begin with the division algorithm or the remainder theorem, as you may have seen it. So A and B are two integers, right? And you can divide A by the integer B, right? And you'll get a quotient Q and a remainder R. Right? So let's also assume that B is non-zero. Then we know that there exists Q and R, both integers, such that you can write A as PQ plus R. So this is essentially what you do when you divide, right? Q times B, and this leaves a remainder R. So this is the quotient, this is the remainder. And
Hello, ma'am. Ma'am, could you speak a bit louder?
Oh, okay. Yeah, now is this fine?
Yes, ma'am, it's better.
Okay, sure. Yeah. So yeah, just let me know, okay, because I might not know. Or if there is any disturbance also, just let me know. Okay, so you can do this division provided that B is non-zero. It's a non-zero integer. You can divide the number A by the number B, and you will get a quotient and you'll get a remainder. Right? And we also know that this remainder is at least 0 and it's definitely less than, in fact, because we are dealing with integers. And this quotient and remainder are actually unique. So this is something is very basic to do. So we are not going to do this. This is also called a remainder theorem. You may have seen this. If you divide one integer by the other, then you get a quotient and you get a remainder. This is called the remainder theorem. So some more notation that we will need. So throughout this lecture, we are going to talk about the greatest common divisor of two integers. So you're given two integers and you want to compute what is called the greatest common divisor. You may have seen this in high school, but we will still define what the greatest common divisor is, why it should exist, and how to compute it. Right? So computation, you want to write down, let's say you want to write down a program, a C program that computes the GCD of two given numbers. Right? That's the goal. Okay. So we said that A and B are two integers. And we will use the notation B divides A. Okay, so this means that B divides the integer A. In other words, there is no remainder upon division. So you can also think about this as A is equal to BQ for some Q on some integer Q. This notation should be clear. And we may also say that B does not divide A, to say that there is definitely a non-zero remainder upon division. Okay. So these are two notations we will use throughout, because we are going to talk about divisors. We will need to say that one integer divides the other, one does not divide the other, and so on. Okay. So what can you say about 1 and A? Let's say A is some integer. So can you say that one divides or one does not divide?
One divides it.
So 1 divides A, minus 1 also divides A. Okay, so these things we will take for granted. So now we want to define the greatest common divisor of two numbers, two integers. So GCD of A, B. Right? So A and B are integers. And we will usually assume that B is non-zero because we want to divide. But we can also actually say that B is. So what do you say about this thing? What can you say about A and 0? Does it divide or not divide? What is your opinion?
A divides 0.
So any number divides 0 and 1 divides every number. So this is something. So GCD of A comma 0 is also fine. So now can someone define the GCD of integers? Like how would you define the GCD formally? Now with this notation. Right? So when you say a number is the GCD of A and B, let's say D. Okay, so D is the GCD. It's a divisor of A and B. If, how would you define this?
Ma'am, first of all, D divides both A and B. And if any other number divides both A and B, then it also divides D.
Right. So is that clear to everybody? So D is the greatest common divisor. Means at first it should be a common divisor, right? So it should divide both A and B. So D divides A and D divides B. And the second point is that it should be the greatest of all the divisors. Right? In other words, if there is any integer Q that divides A and such that Q divides A and Q divides B, then D must be larger than Q in the sense that Q should also divide B. So this is what the greatest common divisor is. Is the definition clear? I'm sure you've all seen this in school. So, okay, so now we understand what the greatest common divisor of any two integers are. So now you can define GCD of 10, 14, or GCD of 2, 6, and so on. Right? You can find the divisors. So one question is, given any two integers, why should the greatest common divisor exist? Right? Why should there be this number? And is it unique? So if I give you two people two integers, will they both come up with the same greatest common divisor? So the first thing is the existence. So why should it exist? Let's say A, B are integers. We want to argue that the GCD of A, B exists. So this might seem like a really simple statement, right? We all know how to compute it. Like you look at A, you look at all its divisors. You look at B, look at all its divisors. Look at what things are common, and then take the greatest one of all. For example, let's just do an example. This might be like really silly in the sense that why are we even doing an example, right? In that sense. So, for example, if you want to compute the GCD of, let's say, 12 and 16, you look at all the divisors of 12. 1, 2, 3, 4, 6, 12. And look at the ones that divide 16. And look at the ones that are common. 1, 2, 4 are common. Of them, the largest is 4. And you say the 4 is the GCD. So there is no great thing about its existence. But how does one formally prove the GCD exists? So can somebody think about it? Like why should the GCD exist? How do you do it? Any clues? It seems like very simple, right? We all know how to compute it, so it should exist. Okay, so let's do this. At least I'm convinced that you are all not sure how to prove this, right? Or have you already seen this? I just want to know that.
We saw something like this in group theory.
You've already seen this in group theory, is it?
Yeah, just the GCD part.
Oh, okay. Okay.
And writing GCD as a linear combination.
So you've seen that and the Zoots coefficients.
Yeah, yes. Both existence and the theorems.
Okay, so I'm not sure how much will be repeated, but
Okay.
I think it's still fine because again, at least the first part of this lecture will be about the Zoots coefficients. Yeah, maybe you can consider it as a refresher. So have you seen the Euclid's algorithm also to compute this CD?
No, ma'am. Like we did it using group theory.
Okay, so then, it's yeah. So we will. So at least from the perspective of computer science, what we want you to understand is that given two integers, you can actually write a program that computes the GCD very efficiently. Right? You should not like do a lot of computation. Easily, you should be able to see. So, for example, if I give you two numbers m and n, you already see that the way we did this here, right, can be very expensive. That is, you have to first figure out what the devices are. So you have to sit and make a lot of divisions. Then you have to find the devices of B. Then you have to see what is common and then look at the greatest one. Seems a very humongous task, right? When the numbers are very large. For example, if it's GCD of 10,000 and 25,000, you have to sit and actually find all the devices of 10,000, devices of 25,000, find the common ones. So it'll take a lot of arithmetic operations. So we want to see if there is any easier way to do this. So for that, understanding even the existence is actually useful. Okay, so then maybe I will just go through this quickly. So when both A and B are 0, we know that the GCD is 0. So there is no big deal. So we can assume that A and B are both positive. Then the negative things work the same way because divisibility is not affected by sign. Okay, so we will look at the set of linear combinations of A and B, where U and B are just integers. In the sense that you will look at integer linear combinations of A and B, such that AU plus BB is possible. We call this set X. And this is a subset of integers because we are only looking at integer linear combinations of A and B. So there must be a well-defined least element. Right? Let D be the smallest element. This is by well ordering. If you remember, we saw this in the first few lectures, right? That any subset of integers well ordered. So there is a well-defined smallest element in the set X. Let's call that set D. So now the claim is that D is the greatest common divisor of A and B. So let's try to see why should it be like this, or why is this set X useful? But you might have seen this set making appearance when you study the Zoots coefficients also. The first thing is that D divides A. So A we know is an integer and D is the smallest element. So let's divide A by D. Right? I want to see whether it divides or not. In the sense, I want to argue that the remainder is 0 when I divide A by D. So you can write A as QD plus R, where R is the remainder. Right? So R is greater than or equal to 0 and it's equal to less than. Now, what can I say about D? D I know is an element in X. So I should be able to write this as UA plus B. So now I can regroup things and I will get minus B. Okay, so this is R, a remainder R. So we assumed that all of these are non-zero, greater than or equal to 0. So if the remainder is greater than 0, the remainder we know is less than B. If it's greater than 0, then what can we say about the remainder?
It belongs to X, and it is less than X.
Right. If yeah, so this right. So this remainder is already of this form, right? AU plus E. So you can actually, it's a linear combination of A and B. So it's also in the set X. Remainder is in the set X, and we know that the remainder is less than B because you, so the remainder you obtained by dividing A by B. So these two things, this is a contradiction to the minimality of D being the smallest element. So this means that the remainder needs to be 0. A should be Q times D. So the same as saying D divides A. Similarly, you can also argue that D divides B. And now for any Q that divides A and Q that divides B, you know that A can be written as A times Q and B can be written as A times Q. So let's look at what D is. A is which means that Q divides D. So this implies that just look at this set, look at the smallest element, and that's the greatest common divisor. Similarly, you can also argue that it is unique up to sign. That is, if there is another D prime that has this, then D and D prime just differ by sign. Right? Okay. So I'm not sure if you saw this proof in group theory. Did you? Just
No, ma'am.
okay. Yeah, this is purely number theory. Like there is nothing. So whatever we see today will use nothing beyond just division. Okay. So now, how do you compute the GCD? We know that it exists. So given two numbers, we want to compute the GCD. In the sense, right? When I say compute, you want to write a program to do this. So here is a simple observation that is observed way earlier. So the procedure that we'll see today to compute the GCD was described by Euclid in 300 BC. So it is written in one of the first books in mathematics. And this is one of the first procedures in number theory. Given two integers and you want to compute the GCD. It's that old. So it should be like super cool, right? You know that. So we are all familiar with these things: A, B, Q, R, and B. Let's take this 1, 0, and these are all integers. And what is the statement that we have? A can be written as QB plus R, that R is less than B, and then it's just division. So now here is one nice observation. So let's take GCD of 148 and GCD of 28. So suppose you wanted to count this, calculate this. What would you do as a first? It's not clear, right? How, given any two numbers, like 10,050 and 20,040, I am just going to throw some numbers at you, and I want you to compute the GCD. How do you begin?
Divide it, take the remainder.
Sorry?
Divide it, write in form that A equal to BQ plus R, and then
and then keep working with it. Maybe there is some way, right? Maybe you can use division. Who knows? Maybe that maybe 28 itself divides 140. We don't. I mean, here you might know because the numbers are small, but generally you don't know whether the numbers one of them divide the other. So we will usually assume that A is the larger number. So we will divide A by B. So that is something I want to say. So here is the observation that Euclid made. So that the GCD of AB is exactly equal to the GCD of BR. Right? So you take A, you take B, you divide A by B, and you get a remainder. Now it's very cool to observe that the GCD of the original two numbers is exactly equal to the GCD of two numbers that are much smaller. Right? So in general, this remainder will be much smaller than B itself. So it will be smaller than A also. So it significantly reduced your problem to compute the GCD of two smaller numbers. Okay? So this is what first we want to prove. So this, I'm not sure if you've seen this in group theory, but whatever it is, you will see a proof that is number theoretic. Okay, so let D be the GCD of A and B. Now, what do I want to argue? I want to argue that this D is the GCD of B and R. Right? So we know that D divides A and D divides B. Right? This is something we know. And I want to show that D divides R and D divides B, which we anyway. Okay. So what is the equation that we have here? Let's begin with that. So we know that A is A times B. And you know that D divides A. So A is some S times D and B is some T times D. So when we say this S, T are all integers. Okay, so any other letters that I use, they are all integers. So for some S, I may not mention them regularly, so you can assume that they're all. So what can you do now? So now what else do you need to prove? That it's divisible. Is this clear by the way? Thought this was simple, so it should be clear. So if I want to prove that D is the GCD of B and R, what is the other thing I should prove?
C divides D and C divides R, then C divides D.
Correct. So let's prove that. So if there is a D prime that divides D prime that divides R, then you know that. Yeah, these are just manipulations. I'm sure you can do it yourself. But just for this example, I will do, and then I will leave others as exercise. So now I want to talk about A. I know that this can be written as QB plus R. So this means that D prime divides A. Similarly, you can also argue that D prime, yeah, and D was the GCD of A. Sorry. So you can argue that D prime will divide because D is the GCD of A. So this tells us this really nice thing that we can now use. The GCD of A and B is the GCD of B and R. So now what was initially like really difficult is now much easier. So now I want to, so let's just do one example and we will use this example throughout to do other things. So I want to compute the GCD of these two numbers. How do I do that? So as we saw first, let's divide 102 by 38. So now I know that the GCD of these two things is the same as the GCD of, so this is my Q, this is B, this is my, right? So now I have to divide 36 by what? The next step. Sorry, not 36, right? It should be 38. Yeah, correct me if I'm wrong, because there are so many numbers. Mess up. Right, so in the first step, you divide 102 by 38, you get a quotient, you get a remainder. Now you have this clue that the GCD of 102 and 38, that's the first step, is the same as the GCD of what two numbers?
38 and 26.
Right, so now you can continue by dividing this. 12, 26, plus 2. Keep doing this. Okay. So now you know that these two things are equal. This is the same as GCD of 26 and 12. It's the same as GCD. Yeah. So in the end, you will get, if you're doing this, you'll get GCD of this is 2 and 0, I hope. Yeah, so you'll get the GCD is 2. Keep proceeding, let's say, and then you'll get that the final answer is GCD of 2, 0. So you keep dividing at every stage by B and R, And the last but one step, right? Whatever non-zero reminder you get, that is your GCD. So this one is the GCD. So when you hit reminder 0, you look at the unwind the previous step. Whatever was the reminder, that's the GCD. Is this clear? Everybody? Otherwise, we'll do some more examples. Like how to compute the GCD, right? So I want to actually write this down as a procedure, right? Because we are interested in algorithms, though you are not familiar with algorithms. So what is the procedure? Right? So the input is 2 integers. The output is GCD. So you continue this for certain steps until you get a reminder as 0, right? So whenever the remainder is non-zero, you keep dividing. At one point, you will hit reminder 0. At that point, you look at the previous non-zero reminder. That is the GCD. Is everybody convinced that this algorithm is correct? It just uses the fact that the GCD of AB is the same as GCD of BR. It's like a really simple observation, nothing fancy. Okay, so in the first step, you do. So the reason I'm writing this down is because we will need this algorithm to compute other things. So it's BQ1 plus R1. That's the quotient in the first step, the remainder in the first step. So this is how you write an algorithm or write a procedure. Right? What is the input, what is the output, and what are the steps? So in the second step, what you do is now you want to divide B by what?
R1.
So B is R1 times Q2. So you do this. In step K, you have so let's say the algorithm or the procedure terminates in K plus 1 steps. So here it was 4 steps, right? So K plus 1 was 4. So in the K plus 1 step, you will get the last remainder, right? So Rk minus 1 is Rk times Q2 plus 0. The moment you hit 0, you know that the previous non-zero remainder was the actual GCD. So you look at the previous step. This person is the GCD. So you will just output. And why does this algorithm terminate? Why does this procedure like end? Why will it not go like infinitely?
Because the remainders are strictly decreasing.
Correct. Because R1 is strictly less than R2. Oh, sorry. The other way, right? R1 is. As you divide, the remainder becomes smaller and smaller. So eventually you will keep this constant. That is infinite number of steps, this will terminate. Although you haven't seen what an algorithm is, this is a procedure, right? I think that much you are practicing. This is a way to compute the GCD. At least it's much better than sitting and finding all the devices, making a common list, and then finding the largest. So this algorithm is called Discrete. To compute this. And just from the observation you have, you can say that the GCD of so so whenever we say a procedure, there are two things we should say, right? First, it terminates. It should not like just keep running. The second thing is it should output the ideal answer, whatever answer we want. So GCD of AB is GCD of R1 and so on, right? So this is with equality. In the end, you will get that this is GCD of Rk minus 1 Rk. This will be equal to GCD of Rk comma 0, which is R. So this, whatever we've written above is the right way to compute this. Is this clear to everybody? Like the notation, whatever, the observation that we did. If there are questions, then we'll take because we have to build on this. Okay, I I'm presuming that you all understand what is going on. So now I think you have already seen what Bezout's questions are, but let's just revisit this once again. Okay? I'm not going to talk about Bezout's question, but we are going to look at whatever procedure we have written here. What happens in this kth step? That's what we want to understand. In step K. So in step K, we have this thing, right? This equation here. Let's write this down again. Okay, we have this equality. So this means that this number here, this integer here, which is the GCD of A comma B, can be written as a linear combination of Rk minus 1 and Rk minus 2. Oops. So now what can you do from this? Given that you have already seen what this expressions are, even if you haven't, if you don't remember what it is, we do it again. But now I've written Rk as a linear combination of the previous reminder, right? So Rk as linear combination Rk minus 2 and Rk minus 1. So if you look at one step above this, what would have happened? You would have had Rk minus 3 minus 1. This is your step K minus 1. So now that I've written this, what can you do about this equation here? Yeah, so just to check, is everything like clear? At least what is going on? One of you, can you just say yes? No?
Yes, ma'am.
Okay. The others also, right? I see many of you answering regularly, so it's fine with others also, right? I don't want to like point names, so just say yes. Somebody.
Yes, ma'am.
Okay. So now what can we say about this? I have Rk minus 1. Just a reminder in this step. So now, just like what we did, I can write Rk minus 1 as a linear combination of Rk minus 2 and Rk minus 3. So I can write so what I have done is I have written, expressed the GCD as a linear combination of the previous two reminders. So I've got gone one step up. So now it should be clear what you should do to express the GCD of A and B as a linear combination of A and B. Can somebody say that? What you should have done one step. So in this step, you will get something like S times R minus 2 plus T times R minus 3. Right? STRs and integers. So what do I do next? So my goal was at least to think about it, to understand what GCD is, how to write, what is the GCD in terms of A and B. Right? That's what I want. So now I have come to, I began with an equation where the GCD was expressed as a linear combination Rk minus 2 and Rk minus 1. Now I have expressed this by substitution as a combination Rk minus 2 and Rk minus 3. So I can keep continuing this, right? Now, if I look at the step K minus 2, that will help me to write Rk minus 2 here as a linear combination of K minus 3 and K minus 4. So I can substitute that. So this way, if I continue, what do I get? I get this is some K times R1 plus L times R2. The last two things here. Now I know that R1 and R2 can be written as a linear combination of A and B. So this is some A times A. Again, R1 here I know is a linear combination of A and B, so I can do that. So I will take after some steps. So this tells me that the GCD of A and B can be expressed as a linear combination of A and B. GCD is RK. And this S and T here, these are called dissociations. And this identity that GCD of A and B can be expressed as an integer linear combination of A and B is called Bezout's identity. So what we did is, did not actually prove, but I gave you a procedure, right, that tells me that by unwinding Euclid's algorithm, this is also called backward substitution, like whatever we do. Right? So there is a way in which you can do backward substitution to obtain the Bezout's coefficients, right, of A and B given any two integers. So if somebody gives you two integers and asks you to tell the Bezout's coefficients, you have to sit and perform Euclid's division, this GCD algorithm. And in every step, you know that there is a remainder, and you can reverse the steps, like use backward computation to write the GCD as a linear combination of A and B. So this S and T are called Bezout's. So what I actually did was prove Bezout's identity, but via procedural step argument. Right? I didn't sit and prove it, but as a proof. But I told you that the GCD can be expressed this way by giving you a procedure. Is this clear? Okay, so whatever we did now, right? I told you write RK minus 1 as this times this and this times this and so on. How do you do this? If you were to program this, you have to sit and write a program for this. How would you do this? When you do it in hand, you can just divide, right? You can divide and keep track of the reminders. This is my RK minus 1, this is my RK minus 2, and sit and like do backward substitution. This thing, right? Then compute this. Write this as, keep this as P, keep this as S, and keep doing this. But when I have to give you a formal way to write it, I have to explain what the various things you have to keep track of. Like for example, at every stage, you have to keep track of the quotient, right? Qi here, Ri, and so on. So just by keeping track of Qi and Ri, you can compute the GCD. Now I want you to output the Bezout's coefficients. So I want you to write down a procedure that will give me this SMT. So there should be some additional effort that we do, right, while computing the GCD. That is what we want to see. So, like, point clear, like what we are trying to do.
Yes, ma'am.
Okay. So this algorithm is an extension of Euclid's algorithm. So you did see, right? First we have to run Euclid's procedure. Only then you know the reminders. Doing backward substitution is only after you get the reminders. So what we are going to see now is extended Euclid's algorithm. So I will just call this procedure because you haven't seen algorithm yet. We will go back to what we did earlier. This thing here. This step. So in step I of Euclid's algorithm, what do we get? In step, let's say I equal to 1 to k plus 1. What we have is this relationship. So this is the thing that we have, the relationship between the current reminder and the previous two reminders. And You run this algorithm for, let's say, k plus 1 steps. What is r k plus 1?
Zero.
And rk is your desired GCD. So these two things we have. The goal here is find ST. So let's say that you ran GCD, this GCD procedure, and it terminated in k step, k plus 1 steps. So the kth step is your GCD. So I want to compute SKTKZ. So that is the Bezout's coefficients, right? These two things. That's what I want to do. Now what we did here, right? At least what I wrote down and did. What did it do? First, it ran Euclid's algorithm. You have to run Euclid's algorithm. So if I ask you to find, so we had an example, right? This GCD of 102 and 50. Now if I ask you to say find the Bezout's coefficients of the GCD. So essentially what you want to do is you want to solve this equation 102x plus 38y is equal to GCD of 102. That you want to sit and solve this equation and find the integer solutions to this. That's what you want. So at least you have to run forward once the whole Euclid's procedure, and then again you have to run once backward, right? You have to look at RK minus RK, write that as this linear combination, sit and do a lot of calculations. So there is one forward pass and there is one backward pass. So now I don't want to do that. Right? So I want to devise a nice procedure. Once when I run the GCD itself, it should keep track of the good things. And in the end, as soon as the GCD algorithm terminates, it should spit out the Bezout's coefficients. So that is the thing. No 2-3 passes. It's a bit messy, right? Sitting and doing this backward substitution. Right? So that's what we want. Right? So now, if you look at this thing here, when I said I equal to 1, some things are not defined. Right? So R1, R2 and all are defined from here. Right? You can divide A by B and see the remainder. Divide B by R1, get the remainder. Those things are all R1, R2. So what is not defined here? When I say I equal to 1, I will need values for R minus 1 and R0, right? So if I put I equal to 1 here, I'll get R minus 1 is R0 cube. R1 I know, but then to keep track of, I should know what R minus 1 and R0 are, right? So that we have to define. So that is something you have to remember. So let us just define R0 to be B and R minus 1 to be B. So in some sense, you can think about it this way. So here is the procedure. You say R minus 1 is A, R0 is B. These are the initialization steps that you do. If you've seen a bit of programming, you might know, right, what is initialization. Then from there on, you can repeat these steps. You can do a division. You can keep track at every stage of what Ri is, what Qi is. Additionally, now, what I want to do is at every step, I want to compute the Bezout's coefficients so that in the end, I can just spit out the Bezout's coefficients. Now, how do you do that? That's the point. Okay. So what do we have after this initialization here? We have that R minus 1 is R0Q plus R1. And R is R. So just that what we did, right? We wrote Ri as a linear combination of these two things, just by changing the other side of the equation. So now I know that this thing here can be written as some Si minus 2 times A plus Pi minus 2 times B. Similarly, this number here can also be expressed like that. So I will just simplify this and regroup, and I'll get A is Si minus 2 times. So now what is the Bessel's coefficients at the ith step? Well, remember that we want to output the Bessel's coefficient the kth step for the GCD. But what I'm trying to do is at every step I'm trying to solve this equation. Whatever is that step's equation, I want to find integer solutions, right? I want to keep track of that so that at the end I can output the Bessel's coefficient. So can somebody figure out what is the Bessel's coefficients at the ith step, or what is the integer that we are interested in? In the ith step, if I ask you what are SITI, such that is equal to SI times A STI times A. Right? What will you output? What will be your answer? So remember that you have done only I steps. So you are sitting down and writing Euclid's algorithm. I steps you have finished writing. So let's say step I is here. Until this you have finished writing. You don't know what comes after this. So only these steps you have done. Steps 1 to I you have done. So you know Q1 to Qi, you know R1 to Ri, and so on. Okay. So now if I ask you, look at the remainder and what is the coefficients, what will you output? What will you tell me? There is output, I'm just asking you. It's already written. So
That SI minus 2 minus SI minus 1.
this one, right?
Yes.
This is your SI and this is your TI. So you can just say SI. Okay, great. So if I ask you what is S3 T3, you can just keep track of this at every stage and tell me the answer without doing any backward substitution. But there is one catch here. Can somebody spot that? This is really cool. So if everything worked, what you will just do is the moment I give you the two integers, you have to do division. Step by step, you will do division. At every stage, you will keep track of at step 1. Let me just erase this. So what you will do is at step 1, you will keep track of Q1, R1, S1, T1, Q2, R2, S2, T2. T3. So now S3 and T3, how do you compute S3 and T3? You know that you can compute S3 as S1 minus S2 times Q3. Cool, right? And to know T3, you don't have to do any effort at all, no backward substitution. Just find out T1 minus T2 times Q3. Keep these, store them in a table. So S3, T3 is done. Store these in a table. Next step, Q4, R4, S4, T2. This you know you can obtain from these two things. Keep doing this. Store these things in a table. In the end, look at the last entry of the table, SK, and output that. Now all this will work modulo one small thing. What is that? Let's see. So this is a recurrence relation, right? So this thing that you have is a recurrence relation. So when I say recurrence relation, what should I define and what is missing? Okay, so how do you compute S1? So in the first step, you have to keep track of some S1 and T1, right? Only then there are other steps you can use that S1 and T1. Now can you say what we need to do to get the procedure right? If you remember, yes, somebody said that.
Now we have to define S right minus.
Right, exactly. So we have defined R minus 1 and R0. So we should define S1 and S minus 1 and S0. So now what is, according to our definition, S minus 1? So it's that form that you can write S minus 1, S minus 1. So now can you define this for me? 0, 3 minus 1. Then that R0 minus 1.
S minus 1 will be 1 and D minus 1 will be 0. And S0,
Is this fine with everybody? Everybody understands this? So what you do is in your table, you will, in your initial table, you will also put this 0, this minus 1, this minus 1, minus 1. All this will be saved. Create an array, save all this, and so that you can use it. And then you are just doing one pass. As you compute the GCD, you are also computing the result coefficients. Right? No forward backward pass. Okay, so as an exercise, you can also sit and compute. Is this clear? Yeah, this is not clear. You should be ready. You should clarify. Anything about the procedure? This is something different, right, from the proof that you saw. It's actually a constructive proof in the sense that you are going to explicitly tell a procedure where you can compute this. So it's a computational algorithm. It might take some time to digest this if you're seeing it for the first time. So go back and look at this. Look at the Euclid's algorithm and try to run some examples. Okay? Look at this procedure. For example, GCD of 102 and 38, explicitly write down what R1, R2, R3 is, do backward substitution, and also try to do extended Euclid's algorithm without backward substitution. Right, so if I give you two numbers and ask you, find out the Bessel's coefficients, you have to write down this procedure and say what is S1, what is T1, and each step. Let's say if there are 4 steps, then at least here, right, there were 4 steps in this example. So here you have to say what S1 is, what T1 is, what S2, T3 are. The final thing that you get. So in step, this is 4 steps. So the third step, the reminder is the GCD. So in third step, if you keep track of S3, T3, that will be your Bessel's coefficient, the GCD. So I hope this is not the proofs that you have seen in the group theory. It's something different. Okay. So what this tells us is that if you look at the equation AX, this always has integer solutions. So now the question is, what about linear equations of this form? When do these have like integer solutions? Remember, we are interested only in integer solutions. Right? And A and B are all integers. When the right hand side is GCD, we know that there exists a solution, and the solution can be obtained by doing the extended Euclid's procedure. What can you say about some D that's not the GCD? So this is something that will require me to do a lot of criteria. So maybe we can do it next time. So these such equations are called Diophantine equations. These equations with integer coefficients, and we are also interested only in integer solutions. We want to characterize when a solution exists or not. So given an equation ax plus by with a, b, integers, right? There exists a solution.
GCD of that should be.
Right. So there exists a solution. GCD B divides. Okay, we used D for GCD, right? So I will use C here. So this if and only if is a really strong thing in the sense that it tells us when or not there will be solutions to given linear equations. For example, if I give you this equation 4x plus 6y is equal to z. What is the condition on z for solutions to exist? Okay? It should be exactly that the GCD of 4 and 6 divides z, which is 2. So you know that all solutions are always even. Okay? Exactly when it's even, there is a solution. Which is very, very nice in the sense that you don't have to look for solutions at all. It really exactly characterizes when solutions exist or don't exist. Okay? And Bezout's lemma is a special case of this when the right answer was just GCD itself. So whatever we saw so far, I mean, we will have to prove this. So this is this. You can try to prove this. It's not a hard answer, but we can also do it. So whatever we did so far tells us how to characterize solutions for linear Diophantine equations. That's what we have done. Okay, so have you seen this theorem already in the group theory class? I don't know.
No, ma'am.
Okay. Yeah, so we'll see this. It's not at all a difficult proof. You can just sit like 5-10 minutes after the lecture and complete it. It will not use anything beyond divisibility. Just try to clear out with the GCD and ABC. That's all. Right? Okay, so this is one application of the Euclid's algorithm. Maybe we'll see one more. I'm not sure, something like Gaussian or something very simple. But I want to remark one thing. So whatever we saw now, right, this extended Euclid's procedure is just doing one pass, right, of the Euclid's algorithm. It's keeping track of a table and then outputting. There's also a matrix based procedure that computes the GCD. It's called, we just write down the name so that in case someone wants to. It's called blank ships algorithm. I'm just avoiding the term algorithm. This is question.
Ma'am, sorry, like actually we have seen the proof of the last state.
So this one, okay, then
Yeah,
great. Maybe let's not do it and spend time. Yeah, if you find difficulty, we can do it. It's not.
Yeah.
Okay, so this blank ships procedure is based on matrix vectors, matrices, and vectors. Yeah, if you have time, you can just go over it. So if this is not part of the course, these are all like quick for that. So there are other ways to compute it. It's not just only extended which is computed. You can take time and take a look at it whenever you're free. So yeah, this is the first part of number theory, the GCD. So in the next lecture, maybe we look at one application. I'm not sure if needed about these Bezout's coefficients. And yeah, this is already a nice application, right? That you can characterize solutions to linear Diophantine equations. And then we will move on to modular arithmetic, like going modulo numbers, just this division, right? There are other ways to look at division. So look at reminders, where reminders really play a role. Like something as simple as division is just used in fabulous protocols that we use today. So we all use the HTTPS dot slash slash. So what actually happens there? Like how is our data being secure? So that is what we want to end the course on number theory with. But for that, we have to build a lot of basics. So all of this you can see as basics towards understanding cryptography. So just to know, have you also seen modular arithmetic in some other course? Yeah, new, so I'm going to ask questions like this.
In group theory, that chapter we had a modular, not in
you had okay, so you have seen this as part of the algebra
basics of
course?
consequences. Yes.
Okay, so basics of theory of congruences you have seen. So fast modular exponentiation, all that you have seen. I mean, I'm throwing terms so that I will get a response, and based on that,
I don't think so.
okay. So yeah, we will do some basic congruence like 5-10 minutes, and then we will move on. So if you have already seen congruences, one question we want to ask is how to solve congruences. I don't know if you have seen this. You should say yes or no.
No, ma'am.
Okay. Yeah, so we are solving linear equations. So we know at least in two variables when this equation is given to us, how do I know the solution? At least the existence of a solution. Now, another question that comes up is when you're given a system of such things, how do you do it? Right? Which you may have seen in the literature. Now, the same thing with equality, you can just replace with congruence and ask. I'm given linear congruences, then can I say that a solution exists? If I'm given one linear congruence, if I'm given like n linear congruence equations, what can I say? So these are what we want to do.
So for the two variable case, the proof of CRT was given. Chinese theorem was given as exercise in article.
So you, when you say this theorem, the one that is displayed on this page, this one, right? This is what you.
Sure.
Yeah, it's a very simple proof. If you want, we can see it 5 minutes after the lecture. I'm sure. If you're not able to solve it, then you have to go back to the lecture. It's that level.
Ma'am, the
So
GCD
please.
of AB has to divide C. I mean, that is a necessary condition because GCD divides the AX plus BY part.
Correct. Yeah. So one direction is this, right?
Yeah, and for the other direction, we just find we find some XY such that AX plus BY is equal to the GCD. And we multiply both sides by C divided by GCD of A, comma B.
Correct.
And we just subtract the two equations.
So the only thing you need is everything should be integers and the remainder should be non-zero.
Yeah.
Okay? Then these divisions you can do. Correct. Yeah. So that is all. By the time we discuss, people are able to solve it. Yeah. If you are not able to do it, we can do it. It's not a big thing, but it's good to get used to writing proofs like this, number theoretic proofs, number theoretic arguments. Okay? So this you can see as a practice. And nothing fancy. Okay? This is an application of finding Bezier functions. That's all. Okay, so we will stop here. Yeah, we will do some other stuff like what I mentioned starting next lecture. I'll just stop recording.
Recording stopped.
Yeah, but if there are questions, then you can.
Ma'am, can I ask a question regarding graph
Uh-huh.
theory?
Yeah, sure. Yeah, which
like-
lecture is this? Is this specific or?
No, yeah, regarding graph theory, like planarity. So if you're
Mhm.
given like a adjacency matrix of a graph, so how
Mhm.
do we have an algorithm to see if the graph is planar or
Yeah.
without
So,
drawing the graph?
yeah, so this whole thing about testing whether a graph is planar or okay, it's a whole field. It's called property testing. In sense, not just planarity. You're given some graph and you want to test some property. Planarity is one property. Right? So there are some algorithms. I mean, deciding it absolutely is based on heuristics. So what they do is you have to search for this subgraph, right? Whether K5 or K3 is things. I mean, irrespective of how the graph is given, it might be given as an adjacency matrix or it might be given as an adjacency list. If you've already seen this, but adjacency list is another representation for graphs. So irrespective of what you have to hunt for K5 or K3 or these forbidden subgraphs. And these are usually based on heuristics. Like for example, if there is a K5, then there are so many cycles. These things. So there is no one decisive algorithm, but there are some algorithms that some heuristic based algorithms that do this. But this is a whole bunch of property testing. I think this might also be after this course. So the best sort of we can do practically. When I mean practically, you should not take like 100 years. Like even factoring, we will see in this course also that if you're given two prime numbers and if they ask you to compute the product, you can just write a computer program that just chucks out the answer in like 2-3 seconds. Now, if I take the product and give this product to some supercomputer and ask it to find the original two prime numbers, it will take 200 years. Considering that these prime numbers are large, like some 100-digit prime numbers. Right? So this way, like exactly turning out yes or no are difficult for some problems. And I say difficult, how much time is required, right? You should not say that after 200 years I will give you the answer. That's difficult one. That's not easy. So property testing is one branch where you will tell it approximately, like with some error, I will figure out whether the graph is planar or not. Or maybe the graph is not entirely planar, but it is close to being planar. So this we did not actually see. It's called the crossing number of a graph. So for example, even K5, if you remember, right, only one edge we could not draw. All but one edge we were able to draw, right, on a plane. So the crossing number of K5 is 1. So this way you can define crossing number of graphs, where what is the maximum extent to which you can make it planar. Some edges you cannot draw, but maybe only 2 edges I cannot draw. Everything else I can draw in a plane. So this is called the crossing number of a graph. So you can design algorithms where you can say the graph is close to being planar, right? It's almost planar except for one edge. So these kinds of algorithms are known to exist very efficiently. They will run really efficiently. But if you ask me to give you an algorithm that always says yes or no in a short amount of time, that will be difficult. Okay, so this short amount of time, efficient, these things will come to you when you do the course and algorithms. Okay, these things are right now unclear. Right? What is short amount of time? So you are all familiar with finite number of steps right now, but we have to define what, when you say a problem is easy or not, based on the amount of time it requires, the amount of resource it requires. So when you say algorithm, eventually you have to like write a program. So you cannot say that after 200 years I will tell you the original two prime numbers. That's not okay. So these things you have to define, like how long is acceptable. So based on those, you can give algorithm. So if you ask me, is there an algorithm? I can say yes. Like, give me 200 years, I can give you the answer. But that's not the way it works, right? So we know algorithms that are efficient that can find a graph, whether a graph is close to being planar. So this is the whole area called property testing. It's not just about planarity. Even any graph, you ask some property, you can ask whether I have an algorithm that tests this property in the graph. Planarity is one.
Okay.
That's some high-level answer. But I think there are some online tools that do this, like Sage or something. You can write programs, but there is a limitation on the number of vertices, number of edges, not a graph. If you have seen Sage before, Sage is a tool in which you can do these codes, like a run codes. Maybe we can try to see, yeah, if there is time in the lecture, how to do this. So GCD and other things you can code in Sage. You can write programs to find the GCD. So these things can be done practically.
Algebra professor is keeping us.
So you are learning Sage, right? Yeah. So yeah, if you're all familiar with Sage, please try to code Euclid's algorithm in Sage and yeah, try to give inputs. So just write the code for this and also basic coefficients. Right? Write an algorithm using Sage that computes the basic coefficients. It'd be really nice. Okay. Yeah, if there are more questions, then we can take. Otherwise, let's meet next Tuesday. I don't think there's a lecture on Thursday.
Thank you, ma'am.
Thank you, ma'am.
Thank you.